Good morning, everyone. Today I'm very happy to share with you our idea, the augmented inertial tracking with inertial sensors. This is a joint work with my colleagues from Dartmouth College, National Taiwan University, National Jiao Tong University, and Columbia University. Inertial sensors are widely used on all sorts of mobile devices, drones, smartwatches, robot vacuums, and so forth. They're often part of the inertial measurement unit, with the accelerometer measuring the acceleration, a gyroscope measuring the angular velocity, and the magnetometer, which can be used to determine the orientation. By integrating those measurements, we can track the trajectory of a device. But output of the sensors includes noises. Although small, they're amplified during the integration, leading to a rapid increase in the location error over time, and this is called the drift problem. Our experiment shows that the tracking error can shoot up to 10 meters within only 20 seconds. The question is, how can we address the drift problem? There are many ways to calibrate the IMU with external landmarks, for example, footsteps during walking, anchor objects in images, GPS locations, Wi-Fi signal strength patterns, or building structure. However, they either require human in the loop or are power hungry, only work outdoors, or are too coarse-grained. In this work, we consider fusing inertial sensors with the ubiquitous light to address the drift problem. Combining the two has many unique benefits. The line offset propagation of light helps to reduce the positioning error to a centimeter level. But light can be blocked and unavailable sometimes, yet IMU readings are always available. Combining the two improves the tracking reliability. Finally, both light sensors and IMU are cheap, small, and low power. They can be easily integrated into everyday objects. Specifically, we propose to generate fine-grained polarization pattern, which is imperceptible to human eyes. If the pattern is known by the device beforehand, it can be used to calibrate the IMU. Before diving into the design, let's review some basics about light polarization. Polarization is the oscillating direction of electric fields as light waves propagate. Usually, sunlight or the light out of a lamp is unpolarized, meaning that the light contains a uniform mixture of different polarizations. To get polarized light, we can put a piece of linear polarizer in front of the light. A polarizer is an optical filter that allows the light waves of a specific polarization to pass through while blocking other polarizations. It's also possible to alter the polarization using so-called optically anisotropic material. Suppose there is a beam of polarized white light which contains light of different wavelength, all with the same polarization. When the light passes through such material, the polarization will rotate by a certain angle. And very interestingly, the angle depends on the wavelength or the color of the light. In other words, such material will disperse the white light in the polarization domain. Yet this dispersion is imperceptible to human eyes. If we look through a polarizer, on the other hand, remember that polarizer only allows a specific polarization to pass through. Then we can observe the light in a certain color. More interestingly, if we rotate the material or change the thickness, we can get a different dispersion, and we will see a different color through the polarizer. Surprisingly, optically anisotropic material is quite common. Everyday transparent tape happens to be one of such material. Let's play with the polarizer and the transparent tape. Here we have two pieces of polarizers. If we place a strip of transparent tape on one piece and look through another, you see the color. And if we put a second layer or slightly change the orientation of the tape, the color becomes different. Actually, if you use your creativity and try more complex tape patterns, you can even create an artwork. So this is not only beautiful, but can also be very useful. If we carefully arrange the transparent tape on the polarizer in grade such that the thickness and orientation of the tape are different at different cells. Then, when unpolarized light passes through such filter, we can get different dispersion patterns at different cells. Furthermore, if we paste this filter to the cover of a light and use 2 Fresnel lenses, which are also very thin, then we can project the polarization pattern in the space. Since only the polarization changes, it's imperceptible to human eyes. For the device to see, we can combine a polarizer and a color sensor on the device. A color sensor is just a set of photodiodes that can sense the intensity of incoming light in red, green, and blue channels separately. And if we cover it with a piece of polarizer, it will see a color. When the device moves across the cells, the sensed color will keep changing. Because we co-locate the color sensor and the IMU, we can use the cell crossing events to calibrate the IMU tracking. Of course, we are faced with several challenges. First, how can we design the polarization pattern? Then how can we detect the polarization pattern reliably? Finally, how can we combine the color and the inertial sensor? Let's begin with the design of the polarization pattern. Because we have only a limited number of tape configurations, we have to reuse them. If we use a color to represent a tape configuration, the pattern design is essentially a coloring problem. And here we have 2 constraints. First, adjacent grades should be colored differently so that the object can detect the cell boundaries by observing the color change. Second, because a single color cannot localize the object, we use a sequence of colors. Therefore, the local color sequences should be unique across the whole map. Here we use a very simple DFS algorithm to generate the pattern. Very briefly, the key idea is to sequentially color each cell with the first color satisfying the constraints. And you can look at our paper for more details. And this is an example pattern. On the right is a filter we created according to the pattern. We cut the tape and paste it on the polarizer manually. And you don't see the color with naked eyes. Again, if you see through a piece of polarizer, you can see the color pattern. After attaching the filter on the light, the next step is to identify the cell crossing using the color sensor. Cell crossing is associated with the color changes, but recall that rotating the receiver can also result in a color change. We must tell them apart. In addition, although ambient light is unpolarized, part of it can still leak through the polarizer and be picked up by the color sensor. Because ambient light can be colored or change over time, we cannot simply subtract a constant offset. To remove the ambient light, we propose a dual sensor design. The key idea is to have 2 color sensors co-located and cover them with polarizers of orthogonal orientations, each sensing the light intensity through the polarizer in RGB channels. Let's take the red channel, for example. The light intensity picked up by the color sensor A is the sum of RA from our light and RA tilde from ambient light. And we have the same result for sensor B. Remember that the light intensity of ambient light is uniformly distributed along all polarization directions. So RA tilde is equal to RB tilde. By taking the difference of the 2 measurements, the ambient light term is canceled out. And we have the same result for green and blue channels. In this way, we can define the differential color values delta C, which is only a metric for the color sensed by the 2 color sensors. Note that the differential color is not affected by ambient light, even if the ambient light is colored or unevenly distributed spatially. Cell crossing can cause the metric to change, but the rotation of the receiver would make it change too. To tell them apart, we need to quantitatively model how the differential color delta C is affected by the receiver orientation theta, which can be obtained from the IMU. Using this model, we can estimate the differential color in each cell for any given orientation. If the observed value always aligns with the estimated, then the object remains in the cell. Otherwise, it's caused by a cell crossing. To derive the model, we can use the Jones calculus in optics, and in the end, the differential color values in each of the RGB channels are a simple cosine function of theta. The parameters B and psi can be obtained from a one-off calibration for each tape configuration, which takes only 2 minutes in our setup and can be reused for different lights. Finally, let's see how we fuse the color and the IMU. We model this problem using Bayesian inference, which is the method of statistical inference. The key idea is to use the differential color as an evidence to continuously update the probability distribution of the object location. Because the model is nonlinear, we cannot derive a closed-form probability density using the popular Kalman filter. Instead, we leverage a sampling-based method called particle filter, which is also widely used. The key idea is to use a collection of particles to approximate the distribution. To give you a more concrete idea, let's see how our particle filter executes in action based on the real data we collected. Here we show the grid map on the floor, and the black circle shows the ground truth position. The color circle shows the tracking result from the particle filter, and the color stands for the measured differential color. The triangles are particles which show the potential positions of the object, and their color shows the estimated differential color at that position. We can see that in the beginning, we locate the object incorrectly. This is because there are multiple cells sharing the same color, and we cannot narrow down to the single cell. However, after a few cell crossings, we determine the cell correctly using a sequence of colors. Also, we can see that the variance of the particles are smaller during cell crossing. We also discussed how this model is extended in 3D tracking. Please refer to our paper for more details. So I'm done with the design. Putting all the design components together, we've implemented a prototype. Which includes a luminary and a receiver. On the light, we added a light cover. With the light on, we can't see any patterns. But if we put a second polarizer, the color pattern will appear on the floor. In our current prototype, the size of each cell is 20 centimeters. This can be more fine-grained if the tape pattern can be created using a more sophisticated process. At the receiver, we add 2 off-the-shelf color sensors. They are tiny and can be easily embedded on mobile devices. And off-the-shelf IMU is co-located. Then we use a Raspberry Pi to stream the sensor data to a laptop to do the fusion in real time. Built-in IMU and microprocessors can also be used if they're already part of the device. To collect the location ground truth, we set up the Vicon system. In our experiment, the tracking target freely moves in the space, and we did the experiment in different ambient light conditions and repeat the experiment for 10 rounds. In the interest of time, let me show you only a few key results. We first look at the accuracy. We compare the 2D tracking accuracy of our method with tracking using only the IMU. The blue line is our method. Here we show the CDF, where the x-axis is the tracking error in log scale. The median error is significantly decreased from about 2 meters to 4 centimeters. Our method performs even better at the tail, with a decrease from more than 10 meters to 8 centimeters. The result shows that our fusion is effective. Then we move to robustness. We also tested our method in the cases with the rotation of the object and the temporary light blockage. The object starts moving from static. While moving, the object can change horizontal orientation. We also emulate a sudden loss of light by covering the light sensors with the hand. Here is the real-time tracking result. The x-axis is time, and the y-axis is the tracking error. When the object starts to move in the beginning, the error is high as the system bootstraps. After crossing some cells, the error drops down quickly. Next, we can see that the tracking error is always bounded during the rotation, which validates our differential color model. Then, during the light blockage, we only use the IMU for tracking, causing an increase in the tracking error. But when the light is back, the error drops down quickly. This experiment shows that our method is robust to receiver rotation and temporary light blockage. We have more results on 3D tracking, ambient light, tracking latency, and the effect on illumination in our paper. Let me conclude with future work. In our current prototype, we augment only one light. We can extend the design to multiple lights, where we can choose a few from them such that their patterns can collectively cover the whole tracking space. Next, in our prototype, we use a point light source, but we can also consider other types of light by customizing the optical design of the lens. Finally, in our experiment, we assume that the object always faces up, but large tilt change can cause significant loss of light, and we can consider adding more pairs of color sensors, each facing a different direction. And thus, we can increase the probability of light exposure. And with that, I'm very happy to take any of your questions.
Okay, let's thank our speaker.
Hi, I'm Karthik from University of Buffalo. You've mentioned 3D tracking a couple of times. Do you track only location or do you track full pose? Can you get the angles in 3D as well?
You mean the angle of the object?
The orientation.
Yes, so currently we receive the orientation from the IMU, but we can use the color to calibrate it. Yeah, because like in the Bayesian model, the orientation of the sensor is also a hidden state in our model, which can be calibrated during the filtering.
One more, if I may. So the experiments you showed is a very small area. How well do you think it can scale?
So currently, each of the cell is 20 centimeters, and in our test bed, it's 6 by 6, so it's 1.2 meters by 1.2 meters. But it's mostly limited by our optical design. So if we can use a better design, we can definitely project the pattern to a larger space. And also, at the same time, if we can create the tape patterns using a more sophisticated process, the cell size will keep the same or even become smaller. Yeah.
Okay, if I can add on to that. So
sure.
In your experiments, of course, you basically have this vertical kind of like the how to say, the patterns are shown vertically. But when you have some other kind of round shaped like a light, like do you see distortion around the edges? Would that be a problem?
So you mean like the lights on the...
So if you have like say round shape or like strange shaped light bulbs, let's say, and then when you cover it, because right now I see like you just put this kind of layer kind of as a flat, like vertical, a horizontal, right? Yeah. But it has to be, if there's any like how to say, weird shape, like in terms of the light bulb, then would that change would that distort the squares you see on the floor? So
you mean the shape of the light? So some shape of the light comes from the light cover. So you mean if the light bulb has some strange shape?
Okay.
So in the beginning, we used 2 pieces of Fresnel lens to regulate the light, such that the light becomes in parallel before it passing through our filter. So we can use optical design to make sure that it won't be distorted. And also, even it's distorted in somehow. But if we know the pattern beforehand, we can still use that to calibrate our result.
Okay.
Yeah.
All right. If no more questions, let's thank our speaker again.